We encounter so many different kinds of forces in our day-to-day lives. There's gravity, there's the tension force, friction, air resistance, spring force, buoyant forces, and so on and so forth. But guess what? Not all these forces are fundamental. Gravity is certainly one of the fundamental forces of nature, but turns out that most other forces that we encounter in our daily life are actually a manifestation of the electromagnetic forces. These are the forces responsible for all the electric and magnetic phenomena and most of the other forces that we encounter in everyday life. But how do electromagnetic forces give rise to all of these? Well, let's get a glimpse of that in this video. Now, there are two parts to these forces, the electric part and the magnetic part. We will save the magnetic part for future videos. In this video, we'll just stick to electric part of it. And even there, we'll talk about a particular kind of electric force, which we call the electrostatic forces. Electrostatic, which we also call static electricity. From the word itself, you can see electro means we're sticking to electric part, and static means stationary, where things are not moving a lot, or maybe they're moving very slowly. The reason to do that is because we want to take baby steps. So first we'll consider what happens when we have static conditions, then we'll see what happens when they're moving, and so on and so forth. Okay. All right. So when it comes to gravity, we'll keep comparing with gravity because we are familiar with gravity. Okay. When it comes to gravity, where does the force of gravity come from? What is it due to? Well, we know that the force of gravity comes from a fundamental property of matter, which we call mass. Things that have mass will produce gravitational force on each other, right? Similarly, what causes electrostatic force? Well, turns out electrostatic force comes from a property of matter called, you've probably heard of this, charge. Anything that has charge will put forces on other things that have charge. Now, an immediate question that we could have is, hey, if that is the case, and if matter has charge, and because of the charge, they put electrostatic forces on each other, why don't we notice that? Why don't we notice electrostatic forces between, say, planets and stars and all of those things? Why don't we notice that in all everyday life? Well, first of all, we do notice them in everyday life, and which we will see in this particular video. But the reason why we don't notice them on a large scale, well, that's a good question, and we'll come back to that. But anyways, if you want to see electrostatic forces in action, it's better to start looking at things inside the atom. So let's do that. We've probably seen the model of an atom. We have the nucleus at the center, which contains protons and neutrons. And we all have, kind of like an electron cloud that surrounds the nucleus, where you have electrons over there. Now, these particles will have charge. Protons have a positive charge. Neutrons are neutral, they have no charge, and electrons have a negative charge. Okay, but we may be wondering, how much charge do protons and electrons have? To answer that question, we need to know the unit of the charge. Just like how mass has a unit of kilograms, charge has a unit of something called the Coulomb, named after the scientist Charles Coulomb, who did a lot of work on this, and the symbol we use is capital C. Now, it turns out that protons and electrons have the same magnitude of the charge. They have different signs, but they have the same magnitude, and we call that number E. And that happens to be roughly 1.602 times 10 to the power minus 19 Coulomb. So it's a very tiny value in terms of coulombs. And so we would now say that the charge on the proton is this much positive, so we'll just call it plus 1e. The charge on the electron is this much negative, so minus 1e. And the charge on the neutron, well, that is 0. It has no charge, so its charge is just 0. And now we can immediately see a big difference between mass and charge. Mass, there's only one kind. But charge, there are two kinds, positives and negatives. And this will now help us understand something. An atom has the same number of protons and electrons, so the total charge of the atoms would just be 0. Because the charge of the proton and charge of the electron will just cancel out. And so the atom itself will be neutral. And so if you consider big objects which has billions and billions of atoms, it's pretty much neutral because the total number of protons is pretty much the same as the total number of electrons. And that's the reason why most things around us are uncharged, or they might have a few extra electrons or protons, so we'll have a very tiny charge, but mostly uncharged, and that's why we don't see electrostatic forces in action most of the time. That's why at celestial scales, we don't see electrostatic forces in action, because they're mostly uncharged or they have very tiny charge. But at the microscopic level, we do see it. We see protons putting forces on other protons and other electrons of the same atom, of the different atom. They're all there. But if you want to study these forces, the next big question we should ask is, what is the strength of this force? How much force would, say, a proton would put on, say, another proton, or maybe on another electron? How do we figure that out? Well, for that, let's assume that we have two, in general, let's consider two charged particles. Let's call these charges as Q1 and Q2. You can imagine, for example, these are two pieces of paper, and these pieces of paper have some extra electrons or some extra protons, let's say. So they are charged, so they will put an electrostatic force on each other. The question we want to try and answer is, what is the direction of that force, and what is the strength of that force? What does that depend on? Let's start with the direction of the force. Positives will push and repel other positives. Negatives will push and repel other negatives. In other words, like charges will repel on each other, but unlike charges will attract each other. A proton will attract an electron. Positives will attract negatives. So the direction of the force depends upon their charge, the polarity of that charge. If both are positive or both are negative, they will repel. If one is positive, the other one is negative, they will attract. For simplicity, let's just assume one. Let's just say that both are positive, then they would repel each other. So this is a repulsive electrostatic force. And now the big question is, what is the strength of this force depend on? Why don't you pause the video and just think about how you think they would be related to Q1 and Q2, the charges, and the distance between them. Okay, since the electrostatic forces come from the charges, we would expect that these forces must be directly related to Q1 and Q2. If either of them increase, we would expect the force to increase. And how would it be related to the distance? Well, if you put them farther away, we would expect the force to become smaller. If you put them very far away, we would expect them to not interact with each other at all, right? On the other hand, if we bring them closer, that means if you make this smaller, the distance to be smaller, you would expect the force to be larger. Closer they are, larger the force, which means you would expect an inverse relationship with the distance between them. Now, if you put it all together, we'll get something called the Coulomb's law, and it looks like this. Notice the Coulomb's law is giving us something very similar to what we predicted. It is directly, the force between the two charges is directly related to the charges themselves. You can see that. And it is inversely related to the distance between them. And more importantly, you can see an inverse square relationship. Where have we seen an inverse square relationship before? Hey, we've seen it in gravity. We've seen the force of gravity, the universal law of gravitation, is very similar. Over here, G, which we call the universal constant, its value was about this much. So what is the value of K, which we call the Coulomb's constant? Well, it turns out that the value of the Coulomb's constant, K, is about 8.99 times 10 to the power 9 units. And can you work out the units yourself? Well, we just have to isolate K on one side. And if you do that, let me do that very quickly. We'll get F times R squared divided by Q1, Q2. So that will be F is newtons, R squared is meters squared, divided by Q1, Q2 is Coulomb squared. Yeah, I don't have to remember them. I never remember them because I can always rearrange and then figure out what the units are. But that's the value of K. And now that you know this, if you know the value of the charges and you know how far they are, we can plug in and figure out the force between them. Okay, so let's quickly compare these two. Well, this one similarity is the inverse square law. The farther you put them, the farther you go, the smaller the force gets. The force dies out very quickly. But what about some differences? Well, the first difference is you can see gravity is only always attractive, but the electrostatic force can be attractive or repulsive. That's because we have two kinds of charges over here, right? But there's another thing that we can see. Look at the value of K. It's much bigger compared to the value of G in standard units. From this, we can kind of guess that the Coulomb's law is much, much stronger than the force of gravity, which means if you take, for example, two protons and compare the force of gravity with the electrostatic force, the Coulomb's force, you will find the Coulomb's force to be way stronger, orders of magnitude stronger than the force of gravity. And so that's why at the subatomic scale, we can completely ignore the force of gravity. It's the electrostatic force that dominates. But as we saw, once we go at a much more larger celestial scale, well, now the masses are so huge and the charges are so small that the force of gravity dominates. I absolutely love this, how at different scale, the different forces dominates. And now we're in a position to understand that. That's incredible, isn't it? But that's not all. Now we're in a position to answer our original question. how electromagnetic forces or electrostatic forces get manifested as some of the daily forces that we see. For example, tension. Where does tension come from? Well, if you were to zoom into a string, you'll see a lot of atoms over there. And although atoms are neutral, because they have positives and negatives inside, they can push and pull on other electrons and protons. For example, the protons can push on the other protons, the protons can pull on the electrons over here can push on the other electrons, the electrons over here can pull on the protons. So there are a lot of forces out there, and we can model and say that pretty much all these forces balance out. They have to, because look, a string is pretty much static. So you can assume that most of the atoms are pretty much static, so they are all balanced, and therefore the net force on all of the atoms are pretty much zero. We say they are in equilibrium. Now, what happens when you pull on the string? Let's say you put a mass on this, attach a mass over here, and because of gravity it pulls on the string. Well, now because of that pull, some of the atoms will start moving farther away from each other. Equilibrium gets disturbed. Net force is no longer zero. It turns out for the string, because the equilibrium gets disturbed and the atoms go away from each other, the net force will try to bring them closer back to each other. And that is how tension force is generated in a string. Isn't that wonderful? It all comes from the electrostatic forces. Similarly, think about, where does the force of friction come from? Well, again, if we were to zoom in over here, we will see that although things look smooth at a macro scale, on a microscopic scale things are not really smooth. And if we zoom in even further, again we will notice that the atoms of the box can interact with the atoms of the floor via the electrostatic forces. And it's these electrostatic forces which all add up and puts and it all adds up and gives rise to the force of friction. Again, it is super complicated. We'll not try to understand exactly how the force of friction comes, why it opposes, say, the force of, why it opposes motion, for example, in some cases. But it all comes from the electrostatic forces. And we can use the same idea, the same model, to explain spring forces, air resistances, buoyant forces, pretty much contact forces, other contact forces that you pretty much see in your daily life. And I find it absolutely fascinating that even though these models are not very accurate, I mean, today we have better, more accurate models, what we call quantum mechanical models, to explain all of these phenomena better. But even if we ignore that, even if we consider, simpler models like we're doing over here, we can just use the idea of the electrostatic forces, the Coulomb's forces, to try and get an intuition behind how it manifests as most of these daily forces that we encounter in life. I find that absolutely beautiful.